In the world of artificial intelligence, pre-trained language models, or PLMs, have become essential tools for tasks like natural language processing. These models, such as BERT and GPT, are trained on vast amounts of data to understand and generate human-like language. However, they come with significant challenges, especially when serving multiple users or tenants on the same hardware. This paper introduces HMI, a system designed to make multi-tenant inference more efficient by managing knowledge hierarchically. The core issue is that PLMs require a lot of computational power and memory. In a multi-tenant setup, where different organizations or applications share the same resources, this can lead to inefficiencies. For example, one tenant might use a generic PLM for broad tasks, while another needs a customized version fine-tuned for specific domains like retail or healthcare. The paper points out that training these models can be done during off-peak times, but serving them for real-time inference is tricky due to their large size and high demands on GPUs. To tackle this, HMI adopts a three-part approach. First, it categorizes the knowledge in PLMs into three levels: general knowledge, which covers basic language understanding; domain-specific knowledge, like details about a particular industry; and task-specific knowledge, which is tailored to exact applications. By analyzing how knowledge is distributed across different layers of a PLM, the system creates hierarchical PLMs, or hPLMs. These are streamlined versions where knowledge is extracted and stored at each level, cutting down on GPU memory usage without losing much accuracy. For instance, imagine a full PLM as a massive library. HMI reorganizes it into a hierarchy. The ground floor has general books everyone can access, upper floors have domain-specific sections, and the top has task-specific materials. This way, tenants don't need to load the entire library into memory. They can pull only what's necessary, saving resources. The second part focuses on managing this hierarchical knowledge across multiple tenants. For domain-specific knowledge, HMI builds and updates knowledge trees based on how frequently certain data is used. This means it only keeps what's popular, avoiding unnecessary storage bloat. For task-specific knowledge, which changes often and requires quick access, the system uses parameter swapping. This technique swaps in and out model parameters on the GPU as needed, keeping everything within limited memory constraints. Finally, HMI includes system optimizations to boost performance. One key feature is fine-grained pipelining with hierarchical knowledge prefetching. This overlaps CPU operations and I/O tasks with GPU computations, so while the GPU is processing one part of the model, the system is already preparing the next. Additionally, it optimizes parallel implementations by batching matrix multiplications, which speeds up inference and improves overall throughput. The paper's experiments show that HMI can handle up to 10,000 hPLMs, like versions of HBERT and HGPT, on a single GPU. This is achieved with only a slight drop in accuracy, making it a practical solution for cloud environments. The authors highlight that this approach aligns with trends in cloud computing, where resources are shared to reduce costs and increase efficiency. In the introduction, the paper discusses how PLMs have led to a homogenization trend, where one model serves many tasks. But in reality, customization is often needed. For example, an online grocery platform might pre-train a PLM on retail data and then fine-tune it for individual stores' needs, like chatbots or product recommendations. This results in numerous model variants, and HMI helps manage them without overwhelming hardware. The workflow involves tenants sending inference requests through a web interface. Challenges include data transfer bandwidth, model swapping times, GPU memory limits, and high computation costs. HMI addresses these by compressing models and pooling PLMs on shared GPUs, as illustrated in the paper's overview figure. Key contributors to this research include Jun Zhang, Zhu Wang, and others from Zhejiang University and the Oppo AI Center. They emphasize that multi-tenant inference is crucial for modern AI services, allowing better hardware utilization and energy savings. Overall, HMI represents a smart evolution in model serving, balancing efficiency with performance in the demanding landscape of pre-trained language models. By leveraging hierarchical structures and optimized management, it paves the way for scalable AI deployments in cloud computing.